Let us now welcome Professor Wilczek with our warmest applause. Welcome.
Thank you. Thank you. It's inspiring to see so many bright young faces.
You can use your earphone.
Yes. And I'm very happy to be giving this lecture at my new home here at SJTU and in Shanghai. So my subject today is origins of mass. The first question you should ask is, what the heck does that mean? Has mass an origin? It's by no means obvious that it makes sense to ask for the origin of mass. In fact, the traditional concept of mass, the concept that was extremely fruitful in the early days of physics, that was introduced by Sir Isaac Newton, indicated that mass had no origin. Newton referred to mass as quantity of matter. So he thought of mass as an intrinsic property of matter that couldn't be taken away. No mass, no matter. This was so basic in his thinking that when he enunciated the famous laws of motion, he didn't even state the most basic law of all, which makes the whole system work. I call it the zeroth law of motion. This is the conservation of mass. It says that every body, every piece of matter has some mass, and if you have a whole bunch of bodies and they stick together, or you regard them as a system, the total mass of the system is just the mass of all the constituent particles, and that total mass stays constant. If that were true, there's no deeper level of explanation. The mass is always the same quantity. It never changes. It doesn't make sense to ask about its origin. It's just something that matter has. This concept of mass served physics very well for over 2 centuries. It was also the foundation of chemistry. Lavoisier, in the experiments that founded chemistry, looked for missing mass in the process of combustion, and in that way discovered the existence of oxygen taken from the air. But over the 20th century, our concept of mass has changed radically. There were, in fact, I would say 4 separate revolutions in our concept of mass. In special relativity, we learned that energy is more basic than mass. So mass is not a primary quality of matter that doesn't change in time. In quantum chromodynamics, or QCD, we learn that most of our mass, most of the mass of our bodies, in fact, is pure energy. We are mostly made out of particles that have 0 mass or almost 0 mass. The vast bulk of our own mass, of our own bodies, comes from pure energy. In the theory of other particles' masses, including the electron's mass, we learn that some important particle masses, not most of the mass of our body, but some very important pieces, comes from the drag of a cosmic medium. And at the frontiers of knowledge today, in cosmology, we learn that most of the mass in the universe is strange and/or mysterious. So in the rest of these lectures, rest of this lecture, I'll say more about each of these 4 things, one by one. So Let me first explain the concept of mass as it's changed in the special theory of relativity and quantum field theory. Now, I hope you won't be too scared by quantum field theory. It takes years to learn properly, but I will not use very much, and I'll tell you exactly, and I won't mathematically derive anything. I will just use some very basic results of quantum field theory. You'll find them very simple to understand, and don't panic. So, perhaps the most famous formula in all of physics is E equals mc squared. And it's not exactly false, but it's kind of misleading. It's a very special statement about the relationship of mass and energy. If you took it literally as E actually equals to mc squared, it would say that the energy is the mass times the speed of light squared, and mass would be essentially the same thing as energy, just multiplied by a constant. But that's not really what the special theory of relativity says. The more accurate version is that associated with any particle, there's its mass, m, little m, and when it's moving, it has moving at some velocity v, it has an energy given by the formula you see there. The energy is the mass times the speed of light squared divided by the square root of 1 minus the velocity squared over the speed of light squared. When the velocity is 0, this becomes E equals mc squared, but that's only a special case. And when you have a bunch of particles together, the total energy is the sum of the energies. The masses do not add, it's the energies that add, and it's also the energy of the whole thing that's constant. So mass now is not the most important quantity. Energy is the most important quantity. Mass is not conserved. The mass of the whole for instance, 2 protons in that picture, in that movie you showed, starts with just 2 protons, and out come zillions of particles. If you added the mass of all those particles at the end, it would be much more than the mass of 2 protons. So the mass is not conserved. Mass is created in such a reaction. But energy is conserved. These are the facts from quantum field theory that you have to realize to understand the deeper discussion that follows. That is that fundamental particles come in units, quanta, of a few kinds. Most notably, the quanta that we're made out of are photons, electrons, quarks, and gluons. The quarks come in 2 types. In a complete accounting of what's in the world, there are many other kinds of quanta, a couple of dozen in all that are known, including neutrinos, Higgs particles, W and Z bosons. But these are the ones that are reasonably stable and out of which we are made. And each of these quanta, each of these fundamental building blocks, has its own characteristic mass. So any 2 photons have an equal value of this mass, little m. Any 2 electrons have the same value, m sub e, and so forth. That's what you need to know about quantum field theory. Particles can also have 0 mass. This was something that wouldn't make sense in Newtonian mechanics. Particles with 0 mass wouldn't know how to move. F equals ma, they'd go crazy. You have to divide by 0 to figure out how to move. And also in the theory of relativity, and in modern physics, they're very special. They can still have non-zero energy, but they must always move at the speed of light, and they obey especially beautiful equations. You'll have to take my word for that, but ask any physicist. They'll tell you. In fact, two of the most famous systems of equations in physics are the Maxwell equations for electrodynamics, which are the equations for massless photons, the particles of light, and the Yang-Mills equations, which are the brainchildren of these two gentlemen, C.N. Yang and Robert Mills, which is a generalization of the Maxwell's equations, which governs the behavior of gluons and which are also massless particles. In fact, I jumped the gun a little bit. I wanted to say that not only are these particles with zero mass special, but nature, and not only are their equations beautiful, but nature likes them too. Photons and gluons have zero mass. Okay, so with that background from the foundations of 20th century physics, now we can discuss the origin of your mass. It actually follows from this version of Einstein's law, E equal to mc squared for a particle at rest. I like to call this Einstein's first law. Einstein's second law is E equals mc squared. There's also a third law, which is c squared equals E divided by m. I call this the first law because this is the one that you'll actually find in Einstein's original paper. In the original paper where Einstein discussed the relationship between mass and energy in the theory of relativity, this is the equation you'll find, not E equals mc squared. And in fact, the title of that paper is, Does the mass of a body depend on its energy content? So right from the beginning, Einstein was thinking of the idea that mass might come from energy stored within the particle. So, some basic facts about you. The mass of atoms is concentrated in their nuclei, these small, dense objects at the middle of atoms. Atomic nuclei are composed, accurately enough for our purpose, of protons and neutrons. But protons and neutrons are complicated objects. This is a snapshot of a proton. It's kind of an artist's impression, actually. But you can take snapshots of a proton using high-energy accelerators and some very clever image processing. And if you do that, you do find that the proton is very complicated. It contains lots of gluons, those are the springs here, and quarks and antiquarks, which are the little balls. Quarks and gluons are the simpler, more fundamental particles from which protons and neutrons are made. Whereas the equations that describe the behavior of protons and neutrons are very complicated, the equations that describe the behavior of quarks and gluons are very simple. They're basically the Yang-Mills equations that I alluded to before. And the theory based on those equations is called quantum chromodynamics, or QCD, and it's been tested very rigorously and very directly in experiments that see quarks and gluons. Now, if you look at a textbook or even read Wikipedia, you may read that quarks and gluons can't exist as free particles. They're always found only inside other particles like protons. But that's not quite true anymore, or that's an obsolete point of view, because I'll show you a picture where you actually can see a quark and an antiquark. what this picture is you have electron and anti-electron colliding at very, very high energy. So coming down this red tube in the middle, meeting and colliding in the middle, and when they collide, their energy associated with their very rapid motion is turned into other kinds of particles. Mass is definitely not conserved, as I said before. But what happens, according to the theory, is often you will produce a quark and an antiquark moving rapidly in opposite directions. So you start with an electron and an anti-electron. With high energy, it becomes a quark and an antiquark with very high energy. Now, quarks and antiquarks can't exist as isolated particles, but according to the formulas of QCD and the phenomenon of asymptotic freedom, what does happen is the quark becomes a whole bunch of things like protons and antiprotons and mesons of various kind, moving rapidly in the same direction. So a quark becomes a so-called jet, which is several particles moving rapidly in the same direction as the original quark, and the energy and the momentum of those particles add up to the original quark, and in the opposite direction you have the original antiquark materializing into its jet, which is also carrying the same total energy and total momentum as the original antiquark. So if you squint and pretend that these jets are single particles and just count their energy and momentum, you're seeing the quark and the antiquark. And the equations that tell you how the quarks and antiquarks behave can be applied to those kind of effective particles. And in that way we get to test the theory. Sometimes in these collisions you have three jets coming out, and in that kind of event what's happened is you produced a quark and an antiquark, and the quark has radiated a gluon. Or maybe the antiquark has radiated a gluon. Somebody's radiated a gluon, and then the gluon makes its own jet. And because you have this very direct window into the underlying basic particles, you can check the equations in great detail. And they're correct. That's how I got my Nobel Prize. Yeah, okay. Thank you. Now, we can also make better pictures of the interior of protons if we calculate, as opposed to doing experiments and counting on artists to make an impression of the experiments. We can actually calculate using the equations. Now that we know that they're correct, we can calculate using the resources of modern powerful computing what the behavior of all these gluons is. And this is what you would see inside a proton if your eyes could work much, much faster and had much, much better spatial resolution than they in fact have. If you could see distances as small as 10 to the minus 14th centimeters and resolve events that happen as fast as 10 to the minus 24th seconds, this is what you'd see. You'd see that in empty space there are fluctuations in the amount of energy in gluon fields, and this is responsible for holding protons together and for a lot of their mass. So let's return from this basic knowledge of how protons are made from quarks and gluons have a compelling theoretical description to the question of the origin of mass. Well, about 120 years ago, Hendrik Lorentz, a great Dutch physicist, famous for Lorentz transformations, among many other things, proposed a visionary theory of the origin of the electron's mass. This was perhaps the first theoretical attempt to really make an account of the origin of mass. It was even before the special theory of relativity. So when I say visionary, it was wrong. It was ahead of its time, but very suggestive and, in fact, partially inspired the theory of relativity. According to Lorentz's idea, if you have a charged particle like an electron, it has electric fields, and if it moves, it also has magnetic fields. Those electric and magnetic fields have energy, and they may resist motion. It may slow things down if you try to move electric and magnetic fields around. And in fact, Lorentz attempted to calculate this effect. According to Lorentz's idea, it's that inertia, that reluctance of electric fields and magnetic fields to move, which slows down electrons and is responsible for the effect we call mass. So you could start with a massless concentration of charge, just calculate the motion of the fields, and produce mass. Well, that never really worked in detail, but it's exactly what happens in quantum chromodynamics, or QCD. About 95% of the mass of protons and neutrons, which is the overwhelming percentage of our own mass, of humans, and of everyday matter in general, arises as the pure energy of quarks and gluons moving around. So they move around inside this proton. That gives them energy, according to the formulas of special relativity. You divide that energy by c squared, and you get the mass of the proton. And this is not just talk. You can actually calculate, using powerful computers and using the precise equations of the theory, the masses of many different particles, many different ways of arranging quarks and gluons that nature can use, and this is what you find. This is a discipline called lattice gauge theory, which allows you to solve the equations of quantum chromodynamics and find what sorts of concentrations of energy of quarks and gluons have a reasonably long lifetime so that they are particles. And you can compare those to the particles that are found in the laboratory, and you find an extraordinarily good agreement. Okay, so there are three inputs to this calculation to fix the theory, but then there's no more room for maneuver. The equations are completely definite, and you have to calculate, and it's either wrong or a great triumph of physics, and it turns out to be a great triumph. Now, among these particles, one of them, N, stands for nucleon. Those are the protons and neutrons. So this calculation, which starts from strictly massless gluons and almost massless up and down quarks, accounts for the origin of our mass. So if you're having trouble with your weight, you think you're too fat and are having a diet, you weigh too much, that's the problem. Now I'd like to discuss a second origin of mass, mass from drag. T.D. Lee, our Shanghai hero and the name attached to our new institute, C.N. Yang, again, and Madame C.S. Wu taught us in 1956 and 1957 that there is a fundamental distinction between left and right. This is what Li and Yang looked like at the time. If they were sitting in this audience, they wouldn't look out of place. And this is what Madame Wu looked like at the time with her equipment. And this is the crucial experiment that she did, which shows the distinction between left and right in fundamental processes. So what it is you have the decays of cobalt-60 nuclei here. You put them in a magnetic field. Cobalt nuclei have a spin, and the magnetic field aligns their spin. And then you find that the direction in which electrons are emitted when cobalt nuclei are decay is preferentially in the direction against the spin. That's the phenomenon. Why does that show that right and left are different? Well, let's think about it. If we have a particle that's spinning, okay, we have some axis, and it's rotating around the axis. Okay? If you change left to right, reflect the thing in the mirror, reflect everything in the mirror, you'll change left to right, okay? And look what happened. The direction of spin has changed. Okay? To match the direction of the left-handed spin, I have to turn over like this. So if you have this experiment and look at it in a mirror, it won't look the same because the spin direction will have changed, but the electron's motion will not have changed. So there's a fundamental distinction in the behavior between the actual experiment and its reflection in a mirror. There's a difference between left and right. To have different behavior for the left and right-handed versions of a particle, that particle must have zero mass. Why is that? Well, if a particle moves at less than the speed of light, first I should say, what do I mean by a left-handed particle and a right-handed particle? When I have a particle that's moving, okay, I have both and spinning, then I have both a direction of motion and a direction of spin. If a particle is spinning and moving so that the spin and motion match the configuration of a right hand, I call that a right-handed particle. If it matches the configuration of a left hand, which is the opposite, I call it a left-handed particle. Now, the phenomenon that Madame Wu observed and was generalized in many other experiments is that the electrons, another phenomenon that occurs, it wasn't originally what she observed, but closely related, is that the electrons that are emitted in weak processes are predominantly left-handed. So left-handed and right-handed electrons have very different behavior. One kind is produced in the decays, the other kind isn't. But to have a distinction between left and right-handed particles, those particles had better be moving at the speed of light. Because if they're moving at less than the speed of light, we can catch up to them, go past them, and if we go past them, their apparent direction of motion is different, although the spin stays the same. So if you move rapidly past a right-handed particle, it becomes left-handed. If there's going to be a fundamental distinction between left and right-handed particles, it better be impossible to catch up to those particles, which means they have zero mass. They're moving at the speed of light. But electrons do not have zero mass. So that was a huge problem. A deep problem brought about by the discoveries of Li and Yang and Madame Wu. The resolution came only many years later. It's by something called the Higgs mechanism. It's a bold idea. It says that, yes, fundamentally, electrons have zero mass. However, They're propagating through space, and space is not empty. Space is filled with some material that changes their properties, that slows them down, a kind of cosmic molasses. Maybe that's an unfamiliar word, but it's a thick syrup that slows things down. Imagine there were a distant planet where intelligent fish evolved. They might think they would eventually develop physics. When they first developed physics, they would have complicated laws of motion because the way things move inside water is very complicated. But eventually, some genius in physics, some genius fish, would figure out that they could get a simpler description of nature, a better description. This fish Newton would realize that you could get simpler laws of motion if you imagine you could take away the water and study things in an emptier environment. So we're like that. We're like those fish. We can get simpler equations, a simpler description of the basic physics. We can make a fundamental distinction between left and right-handed particles if we imagine that we live in a cosmic ocean that slows down the electrons. Now, in the 1960s and 70s, when these ideas were first being explored, physicists quickly realized that no known particle, no known field, not the electromagnetic field, not the photon, not gluons, not quarks, none of those things could construct the medium that would have the required properties to do this job of slowing down electrons. So they postulated a new one. And it got called the Higgs field, after one of the physicists who worked on this problem. It's a wild idea that the universe, and it also sounds like a desperate idea, that the universe is filled with some material so that our equations can be more beautiful. Fortunately, it has observable consequences. The minimal units or quanta of any field appear as particles. So, for example, photons are the quanta of light. They are particles that represent the minimal units of light. Gravitons are the quanta of gravity. Gluons are the quanta of nuclear force fields. If we have this space-filling medium, there has to be some fundamental unit. This is again quantum field theory. There must be some fundamental unit, some quanta of that field. The quanta of the Higgs field is called, without much imagination, the Higgs particle. Since we knew what the Higgs particle had to do if it was going to solve our problems with electrons and other particles, to give them mass, to produce the drag which would look like mass to them, for them, many of the properties of the Higgs particles could be predicted in advance of their observation. We'd seen the field, so we could figure out what the little bits of it, the quanta, would be, and design experiments to look for them. The experiments are not easy, but they're convincing. I won't attempt to convey the details of this, but just to say that the basic process by which the Higgs particle was discovered was inside of protons. As I told you, there are gluons. You shoot protons moving very, very rapidly in opposite directions at one another. This was done at the LHC collider at CERN near Geneva. And theoretically, you can calculate that two gluons can come together, meet a quantum fluctuations quantum fluctuation where you go to heavy particles, top quarks and anti-top quarks. Ordinary matter has very, very feeble couplings because the mass of electrons, quarks, and gluons is very small. So no direct coupling to the Higgs particle, but one of my proudest discoveries, actually, although it's very simple, is that gluons can communicate to the Higgs particle effectively, efficiently, through quantum fluctuations to heavier particles. And then the Higgs particle, in a very, very tiny fraction of a second, decays back by a similar mechanism into photons, and photons are particles we know a lot about. We're familiar with them for a long time, and we can observe them. So in this way, even though the Higgs particle lives only a very short time, it produces photons that are very characteristic, and you can look for them. And here is the actual observation that represented the discovery of the Higgs particle. So when you studied at the accelerator pairs of photons, there are many, many processes that produce pairs of photons, but one of them is a process in which a particle, the Higgs particle of a definite mass, decays into two photons. The energy of those two photons added together must equal mc squared of the original Higgs particle, because energy is conserved. So the energy was mc squared plus a correction for motion if it's moving, and the energy and the photon's energy has to add up to that with a correction if they're moving also. So you should find, if the Higgs particle exists and you organize the plot of events properly, a contribution from the Higgs particle, if it exists, and that little bump, that tiny enhancement over the background of photons produced by other processes, was the discovery of the Higgs particle. A great triumph of theoretical reasoning and our understanding of the origin of the electron's mass. Now let me turn from those stories of triumph to the frontier of knowledge today, where we are still struggling. This, in fact, is most of the mass of the universe, the mysterious dark sector. It might be better to refer to the cosmological dark matter problem as the excess acceleration problem. That's what's actually observed. If we could observe the matter, it wouldn't be dark. It would be something we could study and figure out its properties. And I wouldn't be talking about the dark matter problem. I'd be talking about the particle. I don't know what particle. This doesn't have a name. The Taiji particle, the axion, this WIMP, it's some particle, but it wouldn't be called the dark matter. We'd know what it is. What actually is observed is not a particle or any kind of matter or any kind of interaction of light with matter or any kind of cosmic ray emitted by matter. It's nothing, nothing except that things are moving in a way that they shouldn't be moving. That is, that there seems to be more gravity observed in a whole variety of circumstances than there is matter to supply it. So we think we have very good theories of how gravity works, thanks to Mr. Newton and Mr. Einstein. And we can figure out what the gravity that causes motions of galaxies or planets should be. And things don't quite move that way. There seems to be more matter than than is observed. This excess acceleration, this faster motion, first showed up in analysis of the motions of galaxies within the Coma cluster of galaxies, but by now there are many indications of different kinds. The phenomena are broadly consistent with what's called the cold dark matter hypothesis. That is, that there's a new kind of particle, or perhaps more than one new kind of particle, that interacts very, very weakly with ordinary matter The main interaction is through gravity, but we're also working to find other interactions so that we get a much better, more concrete idea of what this new matter, what this new particle or particles are. Let me briefly indicate a couple of the indications that are especially easy to explain and make nice pictures. So one phenomenon is this. So I mentioned in clusters of galaxies you have excess acceleration. Also within individual galaxies, if you can look at how fast stars are rotating around the center or moving radially, they're different kinds of motion. And you can compare to what what the motion would be due to the gravity of the kind of matter you see. The things like stars, gas clouds, all the kinds of matter that you can see with telescopes, radio telescopes, any kind of astronomical observation that we know how to make today. And what you find is that if you add up the motion of caused by the ordinary matter, you would get this curve, the so-called disk model. That's what the visible matter would predict would be the velocity of stars as they get further and further away from the center. Okay? The velocity would fall because the gravity gets weaker. However, what's actually observed is that the velocities level off and stay constant. If you ascribe this excess acceleration, this unexpected faster motion, to unseen matter, then the kind of matter you infer, the distribution of matter you infer, the so-called dark matter, which doesn't look like this at all. Let me emphasize, you don't see anything. So it doesn't look, this is a fake picture, but it pictures not anything we see, but the theoretical calculation of how much mass there should be. The dark matter is distributed in a very, very broad diffuse halo that extends way, way beyond most of the visible matter. Another phenomenon that arises in the general theory of relativity and has been tested in many experiments now is that matter can bend the path of light. Light is also subject to gravitational fields. And if, therefore, you look at a very, very distant galaxy here, and that the light from that galaxy to get to us has to pass through a region where there's lots of matter, the path of the light can be bent. And as a result, there may be several ways that the light can reach us, in which case we'll see several copies of the object. Distorted, but we'll see several copies, and in general we'll see a distorted looking image of things behind lots of matter. And if you look out at the sky, in some directions you do in fact find very distorted images. So this is just one galaxy, but imaged 5 times, or maybe, I don't know, a lot of times. And you see this one is like become almost a ring of around. And this is due, theoretically, to the fact that the light from these objects has gone through, like a lens, a gravitational lens caused by matter in between the galaxy, the object you're seeing, and us. Like looking through the bottom of a glass soda bottle. And if you calculate how much mass is required to produce the observed amount of bending, again, you find, as in the case of the Coma cluster, as in the case of galaxies, so clusters of galaxies, here also you find that you need much more matter, so-called dark matter, much more mass than can be accounted for in terms of the objects that we know how to observe. So there are several different lines of evidence, all consistent with each other broadly. And the summary can be given in this little pie chart that ordinary matter, the kind of matter that you and I are made out of, the kinds that you'll study in chemistry and biology and engineering classes, the kind that's made out of electrons and photons and quarks and gluons, provides about 4.6% of the mass of the universe. This dark matter that clusters around galaxies and is seen in many other circumstances accounts for about 24% of the mass of the universe. That's called the dark matter. There's another contribution, which actually is the biggest of all, which I haven't even mentioned, the dark energy. And the dark energy is basically the energy, the density of mass itself, of space itself. A great discovery of recent years. Oh, sorry. A great discovery of recent years is that space itself has a tiny but non-zero entropy, non-zero density. And if you add it up in the whole universe, most of the universe is empty of ordinary matter, but this little density adds up and adds up and adds up. Most of the universe is even empty of dark matter, but this stuff adds up and adds up and adds up. And although its density here in this room is very tiny and negligible, added up over the whole universe, it produces most of the mass. The dark matter is what I've been talking about, this stuff that clumps, bends light, holds galaxies together, and holds the coma cluster together, and so forth. Now, the fact that space itself has a density is very interesting, but we don't really know what to do about it, except admire it. So I won't say anything more about that. Dark matter, however, looks like it's some kind of particle, and the question is, what particle is it? And how else can we observe it? So this sets an agenda for research that's very, very exciting and very much in process these days. Physicists have promising ideas for what that dark matter might be, and the hunt is on. I hope in a few years, as a result of activity at the T.D. Lee Center and elsewhere, we'll be able to report exactly what this dark matter is, but all I can do now is show you a couple of the ways that people are looking for some of the more promising candidates. This is a beautiful countryside in Sichuan, where there's a mountain, and in that mountain, a tunnel has been drilled sideways. How long is it? 4.5 kilometers? 17 kilometers into the side of a mountain, so that you're under the top of the mountain, and that protects you from cosmic rays and things that would complicate the observation of very rare events associated with dark matter. But inside that mountain, there are experiments, and a prominent one is the Panda X module that's coming out of the T.D. Lee Institute. And this, in fact, has the world's record for most sensitivity to very interesting kinds of dark matter, the so-called weakly interacting massive particles, or WIMPs, that have a very good theoretical motivation. Unfortunately, so far, the results are negative, but bigger and better detectors will be built inside that mountain, and the hunt is on. Another idea is a particle called axions, very different, with different motivations. It doesn't contradict the WIMPs, but could be another contribution. Personally, it's my favorite. I named it, and I have a lot of fondness for it. Axions would have to be detected in a very different way, with a very different kind of antenna. The basic process is that in the presence of a magnetic field, axions once in a while will turn into photons, and photons we know how to observe. We use a big eyeball like that. Not really, but we know how to deal with photons. So if you can convert, if axions exist, we know that what their interaction should be like. They can convert into photons, and you can search for the photons. So this is another kind of experiment that's being done. You need very, very sensitive detectors. You need to do all kinds of tricks to make this tiny effect observable. But if axions exist and are out there as the dark matter, they should be detected in the next few years. Oh, what am I doing? Another interesting way to look for axions is to look around black holes. Axions would form, uniquely among particles, would form atmospheres around black holes. And now that people are able to study properties of black holes through sensitive astronomical observations, very accurate images, and also through gravitational waves that are emitted when black holes collide, we'll be able to figure out if black holes in fact are surrounded by atmospheres. So stay tuned. I hope in a few years, certainly by the time you're my age, we'll know. So let me summarize. Mass no longer represents rock bottom. In Newtonian physics, it did. It really didn't make sense. It was not a fruitful question to ask about the origin of mass. Mass just was there. It doesn't change. Nothing you can do about it. But no longer is that true. Now we can go deeper. We can discuss in an illuminating way the origins of mass. And we found at least 2 beautiful stories and another one under development. One is that most of our mass is pure energy. That makes me feel good. Some crucial mass, especially the mass of the electron, arises from the drag of a cosmic medium. But most of the mass in the universe still remains mysterious, remains to be accounted for. So thank you.
Please wait a second. Well, thank you, Professor Wilczek, for inspiring and vivid lecture. So, for further interaction, we have prepared this question and answer section. So please raise your hand if you have any questions or ideas to share with us. Yeah, any questions we will do. Any academic, or if you have any question about your life, about your study, it's all okay. So is there any questions? Please raise your hand.
There's
Yes,
one.
yes, please the staff pass the microphone to that one. Thank you.
Actually, I'm not a physicist. I'm a biologist.
Oh, that's okay.
Yeah, but I have long interest from my primary school, medical school, about the physics. It's lucky, like, from your talk, I actually get some ideas, like, similar ideas. I just read some, like, fun book about, the whole mass extra equal to, like, or original from pure energy. But my question is, like, you talk about the original of mass.
Yes.
So how about the original of energy? Like, some people say, okay, it's the whole universe come from Big Bang.
Yes.
So I don't know. I didn't examine exactly. Like,
Well,
but it seems the whole energy expand. The energy expand, and why is that?
well,
Okay.
In the context of special relativity, which governs sort of laboratory scale physics, energy is conserved, so it doesn't make sense to talk about the origin of energy. Just as in Newtonian physics, it didn't make sense to talk about the origin of mass. It was always the same, so you can't change it. So it didn't have an origin, it's just there. In the in a cosmological context, in the context of the whole universe, it's a little bit different. Because when you add up the whole universe, gravitational forces, which are very weak compared to other forces on small scales, add up. What happens is that gravitational binding energy is a negative energy that can make up for the energy of producing particles. So it's a very interesting idea that maybe the energy of the whole universe is zero. But you produce particles and they, by gravitational attraction, have enough energy to account for their mass. So this I've oversimplified quite a bit, but it shows you the kind of ideas that framework in which this question of the origin of energy and the origin of the universe might make sense.
Maybe another question, like we talk about the dark side, or I mean the dark energy, and
Yes.
the I call positive energy anyway. Like, so how this cross-talking with each other, any they are frequently exist. Why so? I mean, it's hard to detect in our words about the dark energy. Maybe because the tech problem. But I don't know how these two sides energy could talk to each other, or
They have no problem talking to each other. They share the same equations. They both exert gravity. The gravity adds up. And both of them are very weakly interacting with each other and with themselves and with other things. So actually, if you take the right course of studies in physics, the actual equations are very simple. They have no problem talking to each other. And they can peacefully coexist very happily. And there's very good experimental evidence for both. The experimental evidence is of different kinds. The main evidence for the dark energy is the fact that the universe accelerates, the expansion of the universe is not slowing down, but rather getting faster. This is an indirect consequence of dark energy, because it turns out that as well as having positive density, a non-zero density, the dark energy exerts negative pressure. And that's a long story to explain why, but that's the important experimental evidence for the existence of dark energy, the most direct. Yeah, I'm not sure exactly what your question is, but I hope that at least addressed it. Yeah. Well, you have three.
Yeah,
three
please
guys.
stop. Give the microphone. Thank you.
Well, my major is journalist. I'm sorry, but so what I want to ask you is about how do you think as a media to report the science research, and how you do your research, because there are so many media just focus on the scientists' private life, but
Right.
not focus on their science research. So how do you think of this problem? Thank you so much.
Well, the question is how to report science.
Yeah,
It's a very broad question, and it is true that people tend. It's much easier to talk about people's personal lives and personalities, and there's nothing wrong with that. But the science is more interesting, mostly. Scientists' personal lives are much less interesting than Hollywood stars and so.
That's
But
it. That's
but
it.
the things they do are much more interesting than sitting in front of a camera and making pictures or singing silly songs. But it takes some patience to learn, and it takes some patience to understand. But it's rewarding, but you have to somehow persuade people that they should make the investment. Well, all I can say is, I try, and my colleagues try. We try to make things as simple, like Einstein said, as simple as possible, but no simpler. I hope I've helped you convey what the dark matter problem is, the idea that mass is no longer the rock bottom in the discussion of matter, that we have a deeper understanding, that we are creatures of pure energy, that there's a medium that fills all space. I mean, these are wonderful concepts that I think can spur people's fantasy and interest and happen to be true. Yeah. All right.
So when you're doing your research, do you the reporter show how you're doing the research to the public?
How do I do them? Well,
like you're doing some experiment.
I don't do any experiments really, I do experiments for fun. They're in my basement, but they're not really experiments. They're making things. No, I mean, to see my work, I think, as it really happens, would not be very interesting to most people. Well, maybe it would. I actually do a lot of my work in the bathtub. I find that very relaxing and kind of private, usually. But most, the work of a theoretical physicist is mostly either talking to people or going to seminars or reading things or calculating. It's not dramatic, except very rarely. I've, in my career of, 25 years now, or 26? No, I'm sorry, 45 years. The number of dramatic moments were perhaps half a dozen, of 5 minutes each. So they might make a good short feature, but not a series. Yeah. So, but the ideas are wonderful. I mean, in all modesty, some of the ideas are really great, and if you explain them in creative ways, people can really enjoy them, I think, and enrich their experience of the world. Yeah. Okay. Yeah.
Please give the microphone to the guy in blue, please. Yeah, you. Because in blue shirt, because he raised hand for quite a long time.
Thank you. Yesterday I attended a lecture given by the president of Osaka University. He told his ideology of co-creation, and I want from the perspective of school manager, and so I want to. I wonder how to where the innovation comes from.
Where innovation comes from?
Can you give us young researchers some advice from the perspective of scientists? Thank you.
Yeah. Well, I gave a long talk about that on last Monday, I guess. Anyway, well, let me just give you a couple of kind of mottos, that because this could be a very long discussion. But I have two mottos that I give to people as things they can remember as advice. Okay, one of them I found in a fortune cookie.
Fortune cookie.
But it really resonated with things I'd been thinking about. It says, "The work will teach you how to do it." And what that means, if you unfold it, is that you shouldn't be afraid to dive in. All discoveries in science were made by human beings, and people that have different kinds of gifts. And I've, you know, in my now that I've won a Nobel Prize, I've gotten to meet a lot of Nobel Prize winners. They're not all so clever. Most of them are not, in fact.
Must be.
So don't be afraid. It was people like you who make these great discoveries, and at some point you have to stop learning things and go for the work. You won't understand everything you're doing, but the process of doing it will teach you. So that's one piece of advice, which is the work will teach you how to do it.
Yeah.
Go with the force. The other is I was asked to give a 3-word summary of myself. Right. At some science conference, people were asked to give three-word introductions to what they do, and I was very proud to, very quick thinking, I found a 3-word summary that's actually infinite, which is a good summary of my career, if I think about it, which is think, play, repeat. So you think, you look out at what's interesting, what are the problems, what looks promising, what doesn't look quite right, and then play with it. Play with the situation, see what occurs if you use ideas that you've used before, or try to put together things in novel ways. And then when something coheres, when something clicks, go deep with it, start thinking, and then repeat. Those are my 2 things. The work will teach you how to do it, and think, play, repeat.
Yes, thank you.
Okay.
Well, maybe we will give some chance to the people on the side. Well, the person in white shirt.
Yes.
Thanks.
Because we all know that there are things called antimatters.
Yes.
So I'm wondering if there are things like anti-energy. If they do, how do they work?
In the current understanding of physics, there's no such thing as anti-energy.
How can you be so sure about it?
What's that?
How can you be so sure about it?
I'm not sure. Well, okay, so let me give two more. I mean, that was a very disappointing answer, I know. But I'll give 2 answers, 2 more insightful comments, I hope. One is a comment I already made, which is that in addition to energy associated with the mass of particles, which was basically always positive, there can be gravitational potential energy, which is negative. So in a sense, that's anti-energy. And you can have positive energy and negative energy canceling off to make 0 energy. So you can have both positive and negative energy, and they can add up, cancel each other to make 0 energy of maybe of the whole universe. So that's one answer. So in that sense, there's negative energy. But if we sort of stick to small-scale things, in quantum mechanics, if there's a process that allows you to lower the energy of a system and radiate, that'll happen. There's in quantum mechanics we have a saying that anything that's not forbidden is mandatory. So quantum mechanics has fluctuations that allow any process consistent with basic principles to happen. So if it were possible to make negative energy, if there were anti-energy, a piece of matter could make anti-energy plus positive energy, and so radiate and lose energy, and radiate and lose more energy, and radiate and lose more energy, and the world would be unstable. So that would be counter to observation and also really bad. So there's a good theoretical reason to think there's no such thing as anti-energy. No.
maybe we can give the microphone to the back. Yeah, the guy in
The way back.
black. Yeah, the way back. In
Way
green.
back.
I'm sorry. Staff, please.
There's a way back.
Thank you.
Thank you, Professor. Your talk is quite exciting. So you notice that we have already found a particle named Higgs particle and its field. Also, you are quite confident and convincing us to be confident that we might discover the theory of what dark matter is.
Yes.
So what do you think that these two kinds of material or energy could affect our daily life? I mean, it doesn't need to be quite fast. Just like, what's the possibility to? Will it make our life to be more science fiction?
Sorry, I just didn't understand at the level
You talked to us several particles that have been found or will be
Yes.
found.
Yes.
So like the Higgs particle. So what can we do about it? What can we
What
do
can
about
we
it?
do about it?
Yes. To do about it.
Well,
to-
we
to-
can
to
admire
put-
it, and we can use it to ask further questions, and who knows what we might stumble into.
Okay.
All I can do is, I don't know what the future will bring, but we can ask similar questions about the past. When people, the electron was only discovered in 1899,
Yes.
I believe.
Thank you.
So when it was originally discovered, it was this funny thing in cathode ray tubes. It was very difficult to make. You had to make a high vacuum and make big fields, and it was very, very unobvious that electrons would ever be good for anything. And today, look around. So we don't know for sure. Now, I really doubt the Higgs particle will ever be as important as the electron, or I really doubt it'll be good for anything. But we have to find out how the world works, and there are many, many aspects to that, and we make better and better understanding, and it comes together, and there can be unexpected consequences that are useful. But useful or not, useful in, the whole concept of useful is very ill-defined. I would say that in my life, the Higgs particle has been very useful. It's given me a lot of joy. And it can do that for you too. So
That's quite useful.
it
Thank you.
could be as useful as, what's supposed to be useful? I don't know. A new car design? Something okay.
Okay, well, as the time is limited, I'm afraid we can have just one more question.
What?
Okay, if you're so eager.
First statement, we are mostly made out of pure energy.
Yes.
So, what do you mean by other kind of energies? Aren't they comprised of? What do you mean with?
What do
other
I mean by
kinds of-
pure energy? Okay, let me. Before
what
you
do
go any further, let me
Sorry.
ask that. Okay, I'm going to answer that question. Okay, so what I mean by pure energy is something very specific. You take a bunch of particles that have zero mass. They can still have energy if they're moving around. And if you have a whole bunch of them inside a confined region, you can add up their energies to make a total energy that's conserved. Divide that energy by c squared. You have the mass of the total object. The total object has been made from pure energy. There was no mass that went into it, just energy.
Yes, but I think you got my question wrong, because as your statement stated, we are mostly made out of pure energy.
That's right.
What do you think of other kind of matters? Aren't they comprised of pure energy?
No,
Why? Do you mean by this statement that possibly Einstein's idea that mass and energy are the two factors of one thing to be wrong in some ways?
I'm not sure I understand the question, but well, okay. My answer would just be to repeat the lecture, so I don't know what to say. Yeah.
Yes, thank you.
Okay, yeah. One more. Let's go. This man is very, very eager. Oh, no, I guess two more. All right.
Hello, Professor. My question is, we know mass can relate to pure energy, but can there be possibility that mass relate to pure space, or energy relate to pure space?
Yes, well, in a sense, I talked before about gravitational binding energy. So there are many forms of energy, some of which are associated with bending of space in general relativity, and or if you like, even in Newtonian theory, there's energy associated with the fields of gravitational fields. So yes, you can have energy in space, energy of space, if you like.
But can space without any mass or energy exist? Just a pure space?
Well, this is a very interesting and profound question, but the modern concept of space in physics is not void, it's not emptiness. It has the Higgs field in it. It has these gluon fluctuations that I talked about in the lecture. It supports electric and magnetic fields. So space is not emptiness. Okay. Again, in Newtonian physics, there was a concept of void. Space was just empty. Newton didn't like that, but it was the concept that was useful in his time. Yeah. In the 19th century, with electromagnetism and Maxwell, we learned that space is not empty. And in 20th century physics, space has been filling up more and more with all kinds of stuff. So we don't think of space as an empty void. It's a medium that has many, many properties and many, many things going on all the time.
Thank you very much.
Yeah, thank you. Professor
Okay, this
Frank.
should be the last, I think, because it's getting... Yeah.
My name is Susanto from Indonesia.
Yes.
Here I'm doing forensic science, especially forensic linguistics, postdoctoral in Shanghai Jiao University. It is interesting to find out your article in MIT. I just read one beautiful sentence in your article. We continue to search for concepts and theories that will allow us to understand the original of mass in all its form by unveiling more of nature's hidden symmetries. I believe that by having this beautiful sentence, you project what will you expect to have.
Yes.
Can you make it in simple way, what you expect in 5, 10, or 50 years by having research on finding out the origin of mass? It is question number one. Question number two, we are young researchers in Shanghai Jiao University. We would like to follow your steps to be a successful, very successful researchers that you are able to get to be awarded a Nobel Prize. So we also, I believe, would like to be like you as a successful researchers. What do you suggest for us? So that's why so that we can follow your steps by steps. Thank you very much.
Okay. Well, the second question I've already answered as much as I'm going to answer in this framework, which is the work will teach you how to do it, and think, play, repeat. Okay, I could give you, well, okay, I'm just going to leave it at that. So your first question was, what do I look forward to in the next 10 or 15 years? And just as for the second part of your question, that was a whole lecture that I gave earlier in my visit here. I think among the things that are related to this lecture that I think I expect, I expect, well, I hope, I'm not sure I expect, but I certainly hope that axions will be discovered and that they will be a big contribution to the dark matter. I hope that supersymmetry will be discovered and some kind of WIMP-like particle will also contribute to the dark matter. I hope for some surprises. I hope in the context of quantum chromodynamics that we learn how to do calculations better so that we can calculate, for instance, the properties of neutron stars and other things we can't calculate today, even though in principle we have the equations for it. And then I didn't mention it in this lecture, but I also hope that we learn in physics to do better justice to the potential of quantum theory. It should give us a very complete description of matter, and we know that we've only kind of scratched the surface of the potential. We want to have quantum computers. We want to calculate more things so that we don't have to do chemistry experiments with smelly and dangerous stuff. Yeah, that's all those things, I think, and more, we want to discover new states of matter, time crystals. We want to continue the beautiful marriage between mathematics and physics that's occurred, especially topology that's occurred in recent years. Build on that. We're in a very interesting period that has enormous potential. And I exercise, I try to eat well, and because I want to stick around for a long time and see these things. Yeah. All right. Okay.
Okay, well, I'm very sorry that we only have this much time because Professor is very busy, and yeah, I'm afraid our Q&A session must end here. I'm so sorry. Well, thank you again for your inspiring lecture and your wonderful answers to these questions. And thank you all for your active participation. I'm so sorry. I understand. Yeah. So first, Professor Wilczek, thank you very much for coming today. We sincerely hope this will leave you a beautiful memory and wish you greater contribution in the future. And let us give our warmest applause to Professor Wilczek again. Thank you. Well, now I have to call the end of the lecture today. Thank you all for coming today. See you next time.